Jupiter, a planet so massive that it exerts influence on the entire solar system. Beneath its swirling clouds lies a mystery we're only beginning to unravel. For centuries, its storms have captivated us, but what lies deeper, underneath the chaos, has remained hidden. Now NASA's Juno mission is about to change all of that. Recent close encounters by Juno have provided unprecedented views of the planet, revealing phenomena never seen before. These images, from intricate patterns of polar cyclones to the ultraviolet glow of auroras sweeping over the poles, offer a key to understanding Jupiter's internal structure and the forces shaping its atmosphere. These images are more than just photographs. They are pieces of data that provide answers to questions that have puzzled scientists for decades. What fuels Jupiter's magnetic field? How does its atmosphere transition from gaseous to liquid? And could its enormous gravity have shaped the solar system itself? Answers to these questions may now be closer than ever. Jupiter's magnetic field is the strongest of any planet in the solar system, more than 20,000 times stronger than Earth's. This massive magnetic field plays a crucial role in the planet's atmospheric dynamics, influencing not only the formation of dark ovals, but also creating stunning auroras. Unlike Earth's visible auroras, Jupiter's can only be observed in ultraviolet light, making them invisible to the naked eye. Both phenomena are caused by the same magnetic interactions, indicating the immense energy passing through the gas giant's atmosphere. The influence of this magnetic field extends far beyond the poles. It shapes Jupiter's vast radiation belts, traps charged particles, and even dictates the movement of its volcanic moon, Io. The interaction of these forces makes Jupiter a unique laboratory for studying the physics of magnetospheres and their impact on planetary atmospheres. The storms of this immense planet have fascinated scientists for centuries. For example, the Great Red Spot has been a constant feature of Jupiter's atmosphere for over 350 years. Recent images taken by NASA's Juno spacecraft show that the storm is shrinking over time, yet it remains large enough to engulf several Earths. Beyond the iconic Great Red Spot, Juno has discovered complex storm structures known as corrugated filamentary regions, typically found at subpolar latitudes. These areas feature thread-like clouds interwoven with broader turbulent patterns. It seems that these filaments represent regions where atmospheric layers are vigorously interacting, creating unique features unlike anything seen on Earth. Jupiter's atmosphere is inextricably linked to its magnetic field. Jupiter's atmosphere is a realm of extreme phenomena. Let's take a closer look at these Earth-sized storms born from magnetic tornadoes. These are phenomena as dissimilar from Earth's weather as the size of Jupiter itself. These storms manifest as dark ovals, first spotted in ultraviolet images from the Hubble Space Telescope in the late 1990s. For decades, their origin remained a mystery, but recent studies have revealed a fascinating link between the planet's powerful magnetic field and these extraordinary atmospheric events. Recent observations by planetary scientists led by Troy Sabota and his team have uncovered the mechanism behind these phenomena. Each dark oval forms in Jupiter's polar regions, places where the planet's magnetic field lines converge and interact with charged particles. These particles, coming from Io's plasma torus, a donut-shaped ring of volcanic material ejected by the moon Io, race along the magnetic field lines. When the magnetic field of the plasma torus interacts with the field lines closer to the planet's atmosphere, friction creates magnetic vortices. These vortex structures, resembling tornadoes, descend deep into the planet's stratosphere, where they lift aerosols, creating a dense haze visible in ultraviolet light. These appear as dark ovals in the images. Planetary scientists describe Jupiter's poles as magnetic tornado alley. Storms appear with astonishing regularity at the southern pole, roughly 3/4 of the time in annual Hubble images from 2015 to 2022, and more sporadically at the northern pole. Unlike Earth's tornadoes, which arise from temperature and pressure differences, the Jupiter counterparts owe their existence to electromagnetic forces. Each vortex forms a storm so large that Earth's entire diameter could fit inside it. The haze inside these dark ovals is extraordinarily dense, up to 50 times denser than the surrounding atmosphere. This density suggests that the aerosols are not only lifted from deeper layers of the planet, but are also actively concentrated through the vortex motion of the tornadoes. While the exact chemical composition remains unknown, the formation process provides a window into the turbulent interaction between Jupiter's upper and lower atmospheres. These discoveries offer invaluable insights into the mechanics of the gas giant's weather systems. The enormous scale of these storms, combined with the unique forces driving them, presents a striking contrast to the atmospheric phenomena we observe on Earth. Looking at Jupiter's turbulent atmosphere and generally at its immense size, one might assume its surface lies hidden beneath the clouds. However, Jupiter is fundamentally different from rocky planets like Earth. It has no solid ground. Instead, its structure transitions from gas to liquid and possibly to a dense, mysterious core at extraordinary depths. Understanding Jupiter's internal structure is key to unraveling the formation of gas giants and the dynamics of our solar system. Jupiter is composed mainly of hydrogen and helium, the same elements that dominate the Sun. Starting from its upper atmosphere, Jupiter's clouds consist of ammonia and water with traces of methane and other compounds. These clouds form the colorful bands and storms visible from space. But as we delve deeper, the atmosphere becomes denser, forming a thick, gaseous layer stretching thousands of kilometers below the surface. This composition hints at the planet's origins. Like the Sun, Jupiter formed from the primordial nebula that birthed the solar system. However, it lacked the mass to ignite nuclear fusion and become a star. Instead, it remains a failed star, preserving its primordial gases, which provide a glimpse into the conditions of the early solar system. Beneath its visible atmosphere, pressure and temperature rise sharply. At a depth of about 1,000 miles, hydrogen begins to behave more like a liquid than a gas. This transition doesn't happen straight away. Instead, it happens gradually, creating what scientists call the largest ocean in the solar system, not of water, but of liquid hydrogen. At this depth, immense pressure, millions of times greater than atmospheric pressure at sea level, compresses hydrogen molecules, forcing them into a liquid state. This liquid layer extends tens of thousands of kilometers, creating a vast and exotic environment unlike anything on Earth. Deeper still, approximately 20,000 miles below the cloud tops, hydrogen transitions into an unusual state known as metallic hydrogen. Under pressures exceeding 2 million times Earth's atmosphere and temperatures over 10,000 degrees Fahrenheit, hydrogen molecules are compressed so tightly that their electrons become free, turning the material into a metallic liquid. Metallic hydrogen is crucial to Jupiter's magnetic field. The free-moving electrons in this layer generate a powerful dynamo effect, creating the strongest planetary magnetic field in our solar system. This magnetic field governs the behavior of charged particles around Jupiter, drives intense auroras, and influences its interaction with the solar wind. Beneath the layer of metallic hydrogen lies Jupiter's core, a region still shrouded in mystery. According to current models, the core may be a dense mix of rocky and icy materials combined with metallic elements. However, recent data from NASA's Juno mission suggests that the core could be partially dissolved, forming a diffused, fuzzy region rather than a solid object. The pressure at the core is staggering, equivalent to 100 million Earth atmospheres. Temperatures reach 35,000 degrees Fahrenheit, hotter than the surface of the Sun. Under such extreme conditions, no spacecraft can directly explore the core, so much of its nature is inferred from the theoretical models and indirect measurements using Juno's gravitational data. Jupiter's internal structure provides insight into how gas giants form and evolve. The transition from gaseous to liquid hydrogen, the presence of metallic hydrogen, and the ambiguous core all point to a complex history shaped by the planet's massive gravity and rapid formation during the early years of the solar system's existence. Understanding these layers helps scientists refine models of planetary formation. For example, Jupiter's theoretical partially dissolved core suggests that collisions with massive planetary embryos could have disrupted the core during its formation. Such findings also offer clues about exoplanets similar in size and composition to Jupiter. Jupiter's massive gravitational field not only shapes its interior, but also acts as a shield for the inner solar system. By capturing or redirecting comets and asteroids, Jupiter reduces the frequency of catastrophic collisions with Earth. This protective role has allowed life on our planet to evolve relatively undisturbed over billions of years. This same characteristic has also enabled Jupiter to amass an impressive collection of moons, of which currently 95 are confirmed. Amalthea, one of Jupiter's innermost moons, has intrigued scientists since its discovery. While not as grand as Ganymede or Europa, its unique potato-like shape sets it apart from other celestial bodies. During Juno's 66 close pass of Jupiter, in addition to capturing images of the planet itself, new images of Amalthea were obtained, offering unprecedented details about this small yet significant moon, its structure, and its role in Jupiter's complex system. With a radius of just 52 miles, Amalthea appears tiny in comparison to Earth's moon. Its small size accounts for its irregular shape, which contrasts sharply with the spherical forms of larger moons. Unlike massive bodies that become rounded under the influence of their own gravity, Amalthea lacks the mass necessary to achieve equilibrium, resembling a fragmented asteroid instead. Juno's images reveal that Amalthea's surface is covered in craters and ridges, likely as a result of billions of years of collisions with cosmic debris. These features suggest that the surface composition may include porous rock and possibly water ice materials, reflecting its origin as a captured asteroid or a fragment from the early solar system. Unlike many moons in the solar system, Amalthea orbits remarkably close to Jupiter, just over 112,000 miles from the planet. This proximity places the moon within Jupiter's intense radiation belt, subjecting it to constant bombardment by high-energy particles. Over time, this exposure may have altered the moon's surface chemistry, resulting in the weathering seen in these images. Additionally, the moon contributes to Jupiter's faint ring system. When meteoroids collide with Amalthea, debris is ejected into space, feeding the gossamer rings, encircling of the giant planet. This ongoing process creates dynamic interactions within the planetary system. Amalthea is part of a group of inner moons, including Thebe, Adrastea, and Metis, that collectively shape Jupiter's rings. These moons provide scientists with key insights into how planetary rings form and evolve over time, especially in an environment dominated by strong gravitational and magnetic forces. The moon's small size and irregular shape suggest it may be a remnant from the early solar system. Its proximity to Jupiter raises intriguing questions about how it ended up in its current orbit. Did Amalthea form from material in Jupiter's primordial disk, or was it a wandering asteroid captured by the planet's immense gravity? The moons of Jupiter are not just icy celestial bodies orbiting a massive gas giant. They are entire worlds of intrigue, potentially harboring vast oceans beneath their frozen crust. Among them, Europa stands out as one of the most promising locations to search for extraterrestrial life in our solar system. Its subsurface ocean, combined with geological activity and potential energy sources, offers tantalizing possibilities for habitability. The Europa Clipper spacecraft, launched in October 2024, represents NASA's boldest step toward exploring Europa's habitability. By 2030, it will begin a series of close flybys, using its instruments to study the Moon's ice shell, ocean, and seafloor interactions. Meanwhile, the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023, is set to arrive at Jupiter in 2031. JUICE will focus on Ganymede, but also study Europa and Callisto, shedding light on icy moons as interconnected members of a larger system. Both missions are equipped with state-of-the-art instruments. Radar devices will penetrate the icy shell to measure its thickness and identify pockets of liquid water within. Magnometers will analyze the induced magnetic fields created by the Moon's salty oceans, providing insights into their size, salinity, and dynamics. These combined observations will refine our understanding of Europa's ocean and its potential to support life. Europa's ocean is estimated to hold more than twice the volume of all Earth's oceans combined. Hidden beneath an icy crust that could be only a few miles thick in places, this vast water reservoir interacts with the Moon's rocky mantle, potentially creating hydrothermal vents similar to those found on Earth's ocean floors. These vents, driven by tidal heating from Jupiter's immense gravitational forces, could provide the energy and nutrients necessary to sustain life. Ganymede and Callisto, although they are less geologically active than Europa, also possess subsurface oceans. Ganymede, the largest moon in the solar system, has a thick ice shell and layered ocean structure that may extend over 100 miles deep. Meanwhile, Callisto's ocean, though less explored, is believed to be relatively stable and offers a different environment for potential habitability. The presence of liquid water is a key ingredient for life, but it is not enough on its own. Salts and organic molecules detected on Europa's surface, likely originating from its subsurface ocean, provide further evidence that the Moon has the necessary raw materials for life. The data gathered by Europa Clipper and JUICE will be crucial for future missions. Instruments on these spacecraft will identify areas with thin ice or water vapor plumes venting into space, offering accessible targets for future probes or landers. These missions may include advanced drilling systems capable of penetrating the icy crust to sample the ocean directly, or robotic submarines designed to explore the liquid environment. Exploring Jupiter's oceanic worlds marks the beginning of a new era in the search for extraterrestrial life. Europa, Ganymede, and Callisto are not just icy moons, but dynamic worlds with hidden oceans that may harbor life. While Europa Clipper and JUICE race toward their destination, we don't have to wait years to explore Europa. Thanks to NASA's Europa Trek platform, anyone with an internet connection can take a stroll across this alien moon today. This interactive site offers a detailed virtual tour of Europa, allowing users to explore its mysterious surface and learn about its geological features. The Europa Trek platform uses high-resolution images captured by Voyager 2, Galileo, and Juno missions to create a comprehensive interactive map of the Moon. Accessible at trek.nasa.gov/Europa, the platform allows users to zoom in on Europa's icy plains, examine ridges and cracks, and analyze craters in stunning detail. By clicking the hamburger icon, you can access the guided tour feature by selecting Landforms of Europa, which showcases some of the Moon's most intriguing landmarks, providing both scientific context and captivating visuals. One of Europa Trek's standout features is the ability to measure distances and surface heights. This function's especially valuable for scientists and educators, offering a tool for remote study of the Moon's geology. Europa's surface is crisscrossed by long, dark lines called linea. These are believed to represent fractures in the Moon's icy crust caused by tidal forces generated by Jupiter's immense gravity. Belus Linea, for example, stretches for thousands of kilometers and is one of Europa's most prominent surface features. The platform also showcases areas with chaotic terrain where ice blocks appear to have broken apart and refrozen in new configurations. These regions may indicate past or ongoing activity beneath the ice, possibly linked to a subsurface ocean. Another noteworthy aspect is the scarcity of impact craters on Europa, indicating a young, geologically active surface. One prominent crater, Tyre, a multi-ring structure spanning 87 miles, provides insights into the Moon's surface age and its response to impacts. As Europa Clipper and JUICE approach their targets, their high-resolution data will likely enhance the platform, adding new layers of information and improving our understanding of Europa's surface and interior. In the meantime, virtual exploration of Europa serves as a reminder of how technology can bring the mysteries of the universe closer to us. Whether through a computer screen or instruments aboard a spacecraft, the quest for answers has already propelled humanity into a realm once thought unreachable, a world of discovery. The solar system is unique 20 to 30% of the time. In similar planetary constellations, the central star absorbs the planets that revolve around it. But if that's the case, why didn't this happen to us? The answer to this question may lie in the largest and oldest planet of the solar system, Jupiter. It is possible that before Earth, Venus, and Mercury, there have been other planets. However, they may have been destroyed by Jupiter, laying the foundation for the current solar system. In fact, what if we told you that Jupiter might have originated outside of our star system? Today we'll talk about the hypothetical migration of the gas giant, as well as the way this may have affected life on Earth. As you know, Jupiter is a huge planet composed entirely of gas, mostly helium and hydrogen. The first studies of Jupiter took place back in the 17th century. However, many aspects in regards to this planet remain unsolved to this day. For example, Jupiter's most notable feature, the Great Red Spot, or GRS, is still controversial in scientific circles when it comes to its origin, length of existence, and color. Jupiter's rapid rotation around its axis, approximately 9 Earth hours, creates lengthy and powerful cyclones and anticyclones that can reach speeds of 335 miles per hour. The Great Red Spot is an anticyclone that has been around for over 300 years. However, the GRS is decreasing. According to NASA, in the 19th century, the size of the anticyclone was estimated to be 25,500 miles in width, but now it is slightly larger than the diameter of Earth, 10,250 miles. The reason for the size decrease of the GRS is still unclear, but NASA scientists suggest that the answer may be some unknown activity in Jupiter's atmosphere, which weakens the wind currents. Another mystery of the GRS is the signature red hue. NASA scientists suggest that the cause of the redness is a little-known colorless gas, ammonium hydrosulfide, and it forms sulfur when exposed to solar UV. What's more, NASA scientist Amy Simon believes that there's a correlation between the intensity of the storm's color and its speed. According to her research, the color of the GRS becomes more saturated when the wind speeds up. In addition to helium and hydrogen, Jupiter's atmosphere contains heavy elements such as nitrogen, argon, xenon, etc. However, these elements could only form at very low temperatures where they mixed with other elements that occur in hot environments. This led scientists to the conclusion that perhaps Jupiter did not originate in the same place that it now occupies in the solar system. This gas giant could have theoretically formed 4 times farther away from the Sun. Jupiter might have been enriched with heavy elements and then headed towards our star, completing its formation. To understand the possible migration of Jupiter, Let's take a closer look at how gas giants are formed. Gas giants form in a similar way to ordinary planets, but with a few differences. After a star is born from gas and dust clouds, the excess material rotates around the star, kind of like giant planetary rings. These rings are known as the protoplanetary disk. This is what the planets are formed from. On average, a protoplanetary disk only exists for a very short time on a cosmic scale, up to 10 million years. The disk consists of 99% gas and only 1% dust. As the dust particles crash into each other, thanks to gas, they stick together and form larger objects known as planetesimals. As they continue to gain mass, planetesimals eventually become planets, asteroids, or moons, depending on the amount of material. Planets with a solid surface are formed closer to the star. This is due to the fact that the radiation released after the birth of the star, it can't push heavy elements that make up the planets, like the stone and metal, very far. Gas giants form away from the star as radiation can push the gas farther away. However, a lot of gas is not enough to become a gas giant. These planets must also have a massive solid core to attract gas. So how do the gas giants form such large nuclei if the building materials do not reach them in the quantities they need? According to the research of astrophysicist Kobayashi Tanaka, these giants can build up large core mass thanks to pebbles that are pulled into the solar system due to the orbit of Neptune. Additionally, the ice particles that are pushed out by radiation as vapors can act as a building material for the core. Finally, it is possible for gas giants to be born outside the planetary system and then migrate into narrow orbits. The hypothesis of such planetary migration is called the Grand Tack hypothesis. The Grand Tack hypothesis by Kevin Walsh of the Southwest Research Institute in Boulder suggests that Jupiter likely originated much farther away from the Sun than its current position and gained its mass as it migrated toward the Sun. Also, this hypothesis suggests the migration of Jupiter may have caused the emergence of the asteroid belt and even the insufficient mass of Mars. According to a study by a team of astronomers at Lund University, the future gas giant may have potentially originated in the outer region of the solar system as an icy asteroid. After 2 to 3 million years, Jupiter likely accumulated a mass almost equal to our planet and began to shift towards the Sun. Researcher Sho Shibata explained that Jupiter may have been about 20 AU from the Sun when the solar system was first formed. Affected by gravity, the gas giant headed towards the Sun. On its journey towards the Sun, Jupiter likely chose a very successful path, which was filled with the material necessary for its development. The streams of gas that were still orbiting the newborn Sun were most likely picked up by Jupiter. The gas giant went in a spiral and took a total of about 700,000 years. Hypothetically, Jupiter may not have been in the same place where it is now. The gas giant potentially occupied the current place of Mars. Over time, Jupiter must have migrated to the new space it now occupies in the solar system. A likely proof of Walsh's hypothesis is a group of asteroids called Jupiter Trojans. These asteroids surround the planet from two sides, the front and the back. While exploring these mysterious asteroids, scientists have been very puzzled as to why the group of Trojans in front of Jupiter is twice as large as the one behind. Thanks to computer simulations, scientists at the University of Lund in Sweden have concluded this is a symmetry and is probably caused by planetary migration. Based on that hypothesis, during the internal migration, Jupiter's gravity widened the particle path, securing more Trojans in front of it. Scientists suggest that the Jupiter Trojans may have been part of the Kuiper Belt,
which is located beyond the orbit of Neptune. These asteroids have the potential to allow scientists to explore materials left over after the birth of the solar system without sending spaceships that far. Naturally, these significant space maneuvers of a giant planet could not have left our solar system unaffected. The most compelling evidence of the grand Tack is Mars. It's possible that without the intervention of Jupiter, the red planet would have been larger than Earth. Mars was formed around the same time as Jupiter, so it had the time and opportunity to accumulate a significant mass. However, Mars is only about 4,225 miles in diameter, and for reference, the diameter of the Earth is 7,955 miles. So Mars is about half the size of our home planet. Jupiter is most likely to blame for this. When the gas giant got close to the Sun, it may have absorbed or dispersed the materials that were intended for Mars towards Earth and Venus. Jupiter's mischief doesn't end there. There is an asteroid belt between the orbits of Mars and Jupiter. It covers approximately 140 million miles. The belt mainly consists of small asteroids, although it also contains several larger bodies. For example, there's a dwarf planet Ceres, as well as large asteroids up to 400 miles across, including Vesta, Pallas, and Hygeia. It is possible that another planet could have formed from this belt. However, according to the Grand Tack hypothesis, its formation may have been prevented by the gravitational forces of Jupiter. Because of the gas giant, the planetesimals were not able to unite and simply fell apart. It's possible that Jupiter may have also dispersed a significant amount of materials in the process of migration. Therefore, even if it were possible to switch off the influence of Jupiter, the mass of the belt would not be sufficient to form even a small planet similar to Mars. Finally, the least apparent but most significant consequence of Jupiter's migration was the likely destruction of the first planets in our system. The solar system is really different from other systems. Many of the known planetary systems similar to ours have super-Earths in their composition. These planets are larger than Earth and consist of either rock or gas or a combination of both. So why don't we have planets like that in our system? Astronomer Konstantin Batygin suggests that such planets may have existed in the early days of the solar system. However, it's possible that Jupiter destroyed the first generation of planets. The gravitational influence of Jupiter, which hypothetically traveled close to the Sun and then back to current orbit where it is now, led to the collision of the forming planets. In fact, Jupiter may have set the stage for the formation of the planets we know and, of course, the planet we live on. However, the formation of planets takes a very long time from humanity's point of view, several million years. Therefore, Mercury, Venus, and Earth continued to develop from an already slightly depleted protoplanetary disk. Delayed formation explains the small size and thin atmosphere, as well as the age difference between the outer and inner planets. Admittedly, it is possible that it was Jupiter that influenced the current structure of the solar system. The annihilation of the first planets and the obstruction of the development of Mars may sound like negative events. However, Jupiter's intervention may have had positive consequences for us. What if we told you that the gas giant's migration probably gave the opportunity for life to evolve on our planet? The mystery of the huge amount of water present on Earth is still unsolved in the scientific community. The oceans could not have come into being at the same time as our planet, since all water would have evaporated due to the very high temperature during Earth's formation. However, water probably existed inside our planet, but there was not enough of it to cover 70% of the Earth's surface. The small asteroids are considered to be the most likely source of water, having contained water in the form of ice. Over the course of its migration, Jupiter may have sent these asteroids in our direction.
Moreover, according to astronomer Phil Plait, in addition to water, meteorites containing building blocks for living organisms, that's small asteroids that reach Earth, such as amino acids from which proteins are formed. Therefore, Jupiter may have been one of the reasons for the origin of life on Earth.
In a way, Jupiter can even be considered our shield to some extent. The gravity of the gas giant can change trajectories of dangerous asteroids and comets, steering them away from Earth. And furthermore, Jupiter is capable of absorbing comets that have the potential to become a threat to other planets. For example, in 1994, the 1.2-mile comet Shoemaker-Levy 9 crashed into Jupiter. If this had reached Earth, all life on our planet would have been doomed. However, in order for water to exist on Earth as abundantly as it does now, Jupiter most likely sent asteroids in our direction. That is, Jupiter does not always protect us. On the contrary, it can also be a source of attack. Professor Jonte Horner of the University of Southern Queensland has determined that Jupiter increases the risk of asteroids colliding with our planet. Nevertheless, if Jupiter had a smaller mass, it would have dramatically increased the possibility of cosmic bodies reaching Earth. Therefore, Jupiter definitely plays an important part in our life, but it also has the potential to harm it. Interestingly, there's another subtle influence that Jupiter has on Earth. The Earth's orbit is almost perfectly circular. However, due to Jupiter's gravitational pull, it can stretch into an elliptical shape. This deformation of the orbit will lead to significant climate changes. The summers become much hotter and the winters much colder. Of course, this does not happen very often, only every 405,000 years. But we're currently in the midst of that cycle. The migration of Jupiter has not yet been confirmed and requires further research. However, it's likely that without the gas giant, our solar system would be completely different. It is possible that without its influence, life on Earth may not have existed at all. In 2021, NASA sent the Lucy spacecraft to explore the Trojan asteroids. Perhaps its expedition will reveal more data to confirm the hypothesis of Jupiter's migration, and may also allow us to study the material from which our universe was formed more than 4 billion years ago. There are few places in our solar system as mysterious as Jupiter. Recent advances in space observations have unlocked the amazing secrets of this colossal gas giant, buffeted by endless storms and cyclones. Today we're going to talk about some of the recent discoveries made by the James Webb Space Telescope and NASA's Juno mission. A world where storms have raged for more than 3 centuries, where winds penetrate in the most intricate and unexpected ways, and where the largest vortex in our solar system may not be as old as we thought. These discoveries offer a glimpse into Jupiter's complex and dynamic atmosphere. Join us to learn about discoveries that are rewriting the history and understanding of this majestic planet. Let's start with the fact that the James Webb Space Telescope recently discovered unexpected and intriguing shapes above Jupiter's Great Red Spot, a storm that's been raging for more than 3 centuries. These previously unseen structures, observed with the near-infrared spectrograph instrument, have captured the scientific community's attention by revealing the complexity and dynamism of Jupiter's upper atmosphere. At first glance, the atmosphere above the Great Red Spot may seem unremarkable, but the sensitive infrared capabilities of JWST have shown otherwise. Scientists have detected complex patterns including dark arcs and bright spots that challenge our previous assumptions. These features are likely caused by a powerful atmospheric gravity wave, a phenomenon in which waves generated in Jupiter's turbulent lower atmosphere propagate upward, altering the structure and radiation of the upper layers. Atmospheric gravity waves are something akin to waves on Earth's beach, which can create ripples in the sand but are much more intense. On Jupiter, they shape the gas giant's upper atmosphere in ways we're only beginning to understand. The tremendous energy and turbulence of the Great Red Spot generate these waves, which then travel upward, affecting the dynamics of the atmosphere. JWST observations have shown that the atmospheric structures over the Great Red Spot consist of different heights, with some regions emitting more infrared light due to the presence of hydrogen in Jupiter's ionosphere. This differentiation in heights and emission is a direct result of the influence of gravitational waves. The region above the Great Red Spot is where Jupiter's lower atmosphere meets its magnetic field, much like Earth's atmosphere meets the solar wind, resulting in spectacular auroras. On Jupiter, this interaction is further complicated by volcanic material from Io, the most volcanically active body in our solar system. These materials, combine with charged particles from the Sun, fuel the Jupiterian auroras and contribute to the complex atmosphere dynamics that we observe. Further study of these gravitational waves is expected to provide a deeper understanding of the energy distribution across Jupiter and enhance our understanding of its atmospheric processes. Future missions, such as the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, will build on these findings. Launched in 2023, JUICE should reach Jupiter by 2031, where it'll make detailed observations of the planet and its ocean-bearing moons. Another ongoing mission, NASA's Juno mission, has made another groundbreaking discovery. Jupiter's atmospheric winds permeate the planet in cylindrical layers aligned with the axis of rotation. This discovery changes our understanding of the atmosphere and internal structure of the gas giant, disproving long-held assumptions and providing new insights into the dynamics of planetary atmospheres. By analyzing data from the spacecraft's radio signals, scientists measure minute changes in Juno's speed as it orbits Jupiter. These changes, influenced by fluctuations in Jupiter's gravitational field, allow researchers to peer beneath the planet's turbulent cloud cover. Using high-precision measurements, scientists applied a mathematical method commonly used for rocky planets to model Jupiter's gravitational fluctuations. This innovative approach increased the resolution by a factor of 4 over previous models and provided a detailed view of Jupiter's atmospheric winds. The study shows that Jupiter's powerful east-west zonal winds, observed in the planet's colorful belts and zones, do not propagate radially in all directions. Instead, they penetrate in cylindrical layers oriented parallel to Jupiter's axis of rotation. The cylindrical nature of the winds was confirmed by comparing 40 gravity coefficients measured by Juno with theoretical models. This discovery marks a significant advance in our understanding of the atmospheric dynamics of Jupiter and similar planets. The cylindrical structure of the winds suggests a more complex interaction between the deep atmosphere and internal planetary processes. Unlike Earth's zonal flows, which are influenced by surface and topography, Jupiter's winds extend deep into its interior, unaffected by solid boundaries. These winds reach a depth of about 1,860 miles beneath the cloud tops, much deeper than previously thought. This has profound implications for our understanding of the gas giant's internal structure and the distribution of energy within the planet. But let's get back to JWST, whose news flow never ceases. The telescope has once again revealed unprecedented details about Jupiter's atmosphere. This time, researchers have detected a high-speed jet stream passing over Jupiter's equator above the main cloud decks, This jet stream, more than 3,000 miles wide, again updates our understanding of the complex dynamics of the planet's atmospheric layers. Using NIRCam, scientists have detected this jet 12 to 21 miles above Jupiter's cloud tops. The jet has a speed of 320 miles per hour, which is twice the speed of a Category 5 hurricane on Earth. The discovery sheds light on how Jupiter's atmospheric layers interact, revealing the complexity of the gas giant's weather systems. Jupiter, like Earth, has a multi-layered atmosphere. However, the dynamics of the gas giant's atmosphere are much more intense. The newly discovered jet stream is located in Jupiter's lower stratosphere, just above the tropospheric haze. This position allows it to influence the weather patterns and cloud formations we observe in the equatorial region of the planet. By capturing images in the near-infrared wavelength range, JWST can observe altitudinal layers with surprising clarity. These observations revealed several wind shears, areas where wind speed changes with altitude or distance. That allowed researchers to track the motion of the jet stream. The JWST data, taken at 10-hour intervals, one Jupiterian day, provided a detailed snapshot of atmospheric changes. Additional Hubble Space Telescope observations taken one day after the data from JWST played a crucial role in determining the baseline of Jupiter's equatorial atmosphere. While Hubble's observations focused on the lower layers, JWST's near-infrared capabilities provide a detailed look at high-altitude features. This dual perspective allowed scientists to measure how wind speeds change with altitude and reveal the presence of significant shifts. The detection of the jet stream was unexpected, as previous observations by ground-based telescopes and missions like Juno and Cassini had not revealed such detailed features. The researchers intend to continue observing Jupiter with JWST to determine if the speed and height of the jet stream change over time. Lee Fletcher of the University of Leicester suggests that the strength of the new jet may be related to variations in the planet's stratosphere and could change significantly over the next few years. This ongoing study may reveal more information about the cyclical dynamics of the gas giant's atmosphere. Jupiter's Great Red Spot, the largest and oldest known storm in the solar system, has long been a subject of fascination and mystery. Recently, new theories have emerged that challenge our understanding of this iconic atmospheric formation, suggesting that the Great Red Spot we see today may not be the same storm observed centuries ago. In 1665, Italian astronomer Giovanni Cassini recorded a giant dark spot on Jupiter, which he called the permanent spot. This feature, perhaps first noted by English scientist Robert Hooke in 1664, disappeared from observations by 1713. For many years, astronomers believed that the permanent spot was the same as the modern Great Red Spot, first observed in 1831 at the same latitude. However, a recent study led by Agustin Sanchez La Vega of the University of Basque Country suggests otherwise. After analyzing the size and movement of these vortices over time, the researchers concluded that it's highly unlikely that the current Great Red Spot is the same as Cassini's permanent spot. Most likely, the original storm disappeared between the mid-18th and 19th centuries, making the current Great Red Spot a younger formation with a lifespan of more than 190 years. Using historical data, Sanchez La Vega and his team performed computer modeling to figure out how the Great Red Spot might have formed. The leading theory is that wind instability in Jupiter's atmosphere created the elongated atmospheric cell we see today. This process involves a complex interaction between the planet's high-speed winds and the dynamics of its atmosphere. One of the most significant observations of the Great Red Spot is its constant shrinking. In 1879, the size of the spot was about 24,200 miles, and that's along its longest axis. Today, it is only 8,700 miles long. This dramatic decrease in size raises questions about the storm's future. Will the Great Red Spot eventually disappear, as Cassini's permanent spot did? The research team plans to conduct further modeling to predict the fate of the Great Red Spot. These models will help scientists understand whether the storm will eventually dissipate, and if so, whether a new vortex could form in its place, continuing the cycle observed over centuries. The study of the Great Red Spot not only deepens our knowledge of Jupiter, but also provides insight into the behavior of large-scale vortices on other gas giants and even exoplanets. This new perspective highlights the importance of continuous observations and advanced modeling in unlocking the mysteries of our universe. Despite the vast differences between Jupiter and Earth, the dynamics of their atmospheres and oceans reveal surprising similarities. Recent research by physical oceanographer Leah Siegelman has shown that Jupiter's gas cyclones mirror the behavior of oceanic structures on Earth, offering new insights into the underlying mechanisms that govern these powerful systems. Jupiter's atmosphere, often described as an ocean of gas, exhibits cyclonic activity driven by convection, and that's similar to storms on Earth. Convection is the process by which heat is transferred through fluid motion, and it plays an important role in both terrestrial and Jupiter weather systems. On Earth, convection occurs in both the atmosphere and oceans, creating storm fronts and ocean currents. A study by Siegelman, who analyzed data from NASA's Juno spacecraft, has identified filaments, wispy tendrils, between Jupiter's vortices. They behave similarly to fronts in Earth's oceans and atmospheres. These fronts, characterized by boundaries between masses of different densities, are crucial to the generation of strong winds and currents. On Earth, these density differences are usually due to variations in temperature and salinity, whereas on Jupiter they arise from temperature differences in the gaseous layers. By calculating the horizontal and vertical wind speeds of these infrared images, Team Siegelman confirmed that they contribute significantly to the energy dynamics of Jupiter's cyclones. These filaments help transfer thermal energy from the planet's interior to its upper atmosphere, which accounts for a significant portion of the cyclone's total kinetic energy and vertical heat transport. The presence of convection and fronts on both Earth and Jupiter suggests that these physical mechanisms are fundamental to turbulent fluid bodies throughout the universe. This finding implies that similar processes may exist on other planets with atmosphere or fluid layers, expanding our understanding of planetary science. The comparison of Jupiter's gas cyclones with Earth's oceanic structures provides a basis for the study of other celestial bodies. The ability to draw parallels between such different environments emphasizes the universality of certain physical principles, regardless of specific conditions. The advances in our understanding of Jupiter provided by the JWST and Juno discoveries not only expand our knowledge of the planet, but also set new standards for what can be achieved with advanced space telescopes and probes. High-resolution images and detailed data have revealed previously unseen structures and dynamics in Jupiter's atmosphere. These discoveries pave the way for future missions and exploration. Planned missions such as the European Space Agency's Jupiter Icy Moons Explorer will delve deeper into the Jupiter system, focusing on its moons, Ganymede, Callisto, and Europa. The purpose of these missions? To explore the potential habitability of these moons and further unravel the mysteries of Jupiter's atmosphere. Future space telescopes and probes will have more advanced sensors, enhanced data processing capabilities, and more sophisticated observational techniques, enabling even more detailed and comprehensive studies of distant planets and their atmospheres. By continuing to study the features of this gas giant and its similarities to our home planet, scientists will be able to better predict and model the behavior of the atmospheres of other planets, which of course will expand our knowledge of the cosmos and subsequently help in the search for habitable worlds. The journey is just beginning. So stay tuned as we continue to bring you the latest news and discoveries.